Hello all, I'm Yogesh Singh and welcome to my YouTube channel Yogi's Data Lab. So today we are going to cover a very important topic, feature engineering. Now what is feature engineering? What do you understand by feature engineering? Now feature, as we all know, is a column or a variable of a data set. But why do we need feature engineering? So what we often do in machine learning is we get the data and we start putting the algorithm on the data with minor changes, cleaning your missing value imputation, outlier treatment and all. But sometimes the data doesn't have enough patterns for any algorithm to hold on to it. So what we need to do is we need to go ahead and extract those points from the data, which is not self-explanatory, by combining a couple of features. When I combine a couple of features, possibly those new columns or new features or variables that I created turn out to be important towards the algorithm, and it gives us much better results. So what we are going to cover today is we are going to cover feature engineering, and we are trying to understand if by doing feature engineering, does it help me improve the result, and what type of feature engineering we should do. Okay, so here we are going to take a case study of vehicle insurance losses. So there's a very basic data set where I am going to predict insurance losses for a company, insurance company, or amount of claims which people are going to do for their vehicles, right? So we are going to do it in two steps. The first step is we are going to pick up the original data set and build a model on the original data set alone and look at the matrix. And then we are going to do some feature engineering on the data. And we are going to build a model on the feature engineered data and compare the matrix of the original and the featured one and see what is the difference in the results. So let us start. So what we are doing is we are looking at the basic packages. We have imported NumPy, Pandas, Matplotlib, and Seaborn. I'm reading my Excel file and I'm creating a shallow copy of my data. So I look at the head and the tail. I do see policy number, age, years of driving experience, number of vehicles, gender, whether the person is married or not, vehicle age, fuel type, and losses. Now, when I look at these part, what does it show me? It shows me that the data is pretty clean. Policy number is something which I'll not require because it is not going to contribute. And losses is my target variable where I see I have continuous values. So I'll go ahead with linear regression. I'm not going to do the basic EDA and all, which is a part of any project that we do, assuming that things are fine. But when you work into a project, you should be doing the EDA and everything. This is just concentrated more into feature engineering. So I'm going to clean the data a bit. So I'm going to drop my policy number. As you said, it is not contributing anything towards the losses. So I've dropped my policy number. And I look at my target variable, which is losses, and I go ahead and do a histogram plot of the losses. And it shows that this data is skewed towards the right, which I can pretty much see. So rather than going with this variable, because linear regression is impacted by the outliers. So what we are going to do is we are going to normalize that using log. So I have done a log transformation on the losses variable and created a new column called norm losses. Now, if you look at this, a new column has been created, which is norm losses. And I can go ahead and drop the losses column. Okay, so we are going to drop the losses column. And now, since my data is pretty much ready, I'll create two copies of it. One is the original copy and the another is the feature engineered copy. So in the original copy, I'm going to build a model directly on this data set. I'm not going to do any changes. And on DFFTE, as you see, what I'm going to do is I'm going to do certain feature engineering, and then I will build a model and we'll see exactly how it works. Okay. Well, if you plan to go ahead and try this out, I have shared the link in the description. I put the files and the data file and the code file both on GitHub. You can download it from there and try it out. Now, let's start building a model with the original data. So I have used train test split linear regression. The matrix I have used is only R square and root mean square error, which we call as RMSE. I'm not using the other matrix because I'm again sticking back to the feature engineering part. So I didn't go into MAE, MSE and all this. We are looking at the head, fine. Now, I'll split the data into independent and dependent data set. So I have my independent data set over here. I'm dropping my norm losses and this becomes my independent data set, which is x underscore org. And y underscore org has my original norm losses. I'll create my dummy variables and I have created them. I see that I have all my numerical values over here. There's no categorical anymore. So I'll go ahead and do a train test split. So what I'm doing is I am doing a split where my X org train and Y org train is 70% of the data and 30% of the data goes into test, which is X original test and Y original test. I set the seed as random state equal to 1. Now I'm using linear regression, the sklearn linear regression, and I'm fitting it on the train set. When I do this, the model is done. And what I'm doing is I am predicting it on the original train set and the original test set to get my predicted values. Once I have my original values, my Y train, Y original train, and I have my predicted values over here, I can calculate my R square that is coming on the original data for the train and the test set. So this is what we have done. And I can see that the original R square comes out to be somewhere around 0.54 approximately, which means that I am able to explain around 54% variation in my data, right? So if I'm able to explain 54%, obviously not a very good result, but a decent result, and the model is not overfitting. Why? Because the train and test are very close by in terms of R square. Let's look at RMSE, which is the root mean square error. And when I calculate the root mean square error on the uh, original train and original test, I do see it as 0.49 and they are also very close by. So this was the result on the original data set. Now let us try to have a look at feature engineering. What we are going to do is we are going to create certain features. Now, as I said, when we are creating features, we'll need again a couple of things. We'll look into the math stats part of it, some understanding, and we'll also look into the functional part of it. So functional is very important because I don't want to end up creating features which have no meaning towards business, right? So it has to have some explanation to business. So we are going to look into it. So if you look at this, this is the DFFTE data which we had used. And now what I'm doing is I'm going to go ahead and look into years of driving experience. This is a continuous numerical variable. So what do I look at is I have 25% of the data till 6. Then from 6 to 50% I have 23. And then obviously I have plenty of data over here, which is in the remaining 50%. So what we have done is we are going to take the years of driving experience. And with the years of driving experience that we have, we are going to break it into low, medium, and high. So from 0 to 6, it's going to be low. From 6 to 23, medium years of experience, and obviously greater than 23, we are going to call it as high experience of driving. So when I go ahead and look at this, you see I have a new column, driving experience, which is low, medium, and high. Now the next column that I pick up is the vehicle age. So I do a description. I see 0 to 9 years is 50% of my data, and from 9 to 15, I have another 50% of my data. So what I'm going to do is I'll create it into two bins, new and old. Generally, we observe that until 10 years, the cars are good or the vehicles are good if driven properly. And beyond 10 years, they start demanding some maintenance and the maintenance charges are high. So just taking that into consideration, we have gone ahead and created two labels over here for vehicle age category. So that's a new column that we are creating. So you see a new column is created, which is vehicle age category, which has two values, new and old. Right? So what we did is for now, we split the data into categories and numerical value. Now question comes in, should I go ahead and drop the original column when I create a new categorical column or a new numerical column? You have an original variable and you are creating a new variable which is directly linear to it. In that case, you need to go ahead and drop the first one, the original one, if you want to keep the other one. If not, you can leave it as it is, and both the variables can be passed into the algorithm. Okay. Now let's look at the indicator fields. Now these are indicator fields. What are indicator fields? Indicator fields are the features which are created by combining multiple features together. So I do have a feeling that old vehicles, be it diesel or be it petrol, could be claiming more because they wear out. So we have created new column called old diesel. Wherever the vehicle category is old, means it is greater than 9 years of age, and the fuel type is diesel. And vehicles which are greater than 9 years, which are classified as old, and they are petrol type. So these two are two new columns which we have created, which you can see here. So this was in fuel type B and old, so it came as a 1 in old petrol. So it is an indicator field that we created. Similarly, we'll go with single males and single females, assuming that the singles do claim more. So what we are doing is we are creating with a new column called single males, which is again a combination that gender is male and the person is single, along with another column single females where the gender is female and the marital status is single. So we see that we have created these columns over here. Now, since we have gone ahead and cut the variables and put them into categories, the numerical ones, and now we have created a indicator fields, we'll go with the third type, ratio variables. Now let us try to understand what are ratio variables. So ratio variable is when you divide one variable with another variable and create a new variable. So here what we have done is we have taken vehicle age divided by years of driving experience. Now let's understand this, why I took this concept. So if I say vehicle age, okay, so let's say this number is less, the vehicle is new. So if the vehicle is new and there's a new driver, right? So the years of experience will be less here. So this divided by this is going to be a higher value as compared to a new vehicle with a higher years of experience. So the risk value for a person having higher years of experience on a new vehicle will be comparatively lower as compared to a new vehicle with a new driver. So the risk value will be high here. In case the vehicle is old. So what happens in case the vehicle is old? The vehicle is old, the driver is new. So a larger number divided by a smaller number will get the risk value high. If I have a larger number, old vehicle and an old experienced guy, this value will be comparatively smaller as compared to a new driver, right? So we are creating a new column called risk value, which is again a ratio variable. But you would see that I've added one over here. Now, I was trying this out. What happened is there are a couple of vehicles which are very new and we get a zero. So zero divided by any number is a zero. So the risk value becomes zero. In the other case, what happens is the years of driving experience is zero and I end up with the risk value as infinity. So to avoid this, what we did is we added a one to the numerator and one to the denominator. So this is not exactly what we call as Laplace correction, but pretty much taken the hint from it and done this, where if my vehicle weight is zero and I add a one to it, I will not get any zeros in the numerator. And if my years of driving experience is zero and I add a one to it, I'll never get an infinity in my risk value, right? So we have created this and you can see the risk value has been populated here. Now, once I have all these features, I'll start building a model. Okay, so this is a couple of features that we created. So after norm losses, if you look at this, driving experience, vehicle age category, old diesel, old petrol, single male, single females, and risk value. These are certain columns that we created from these columns that we had received, right? These columns we had received earlier. Now, let us build a model. So again, the same process. I am going ahead and separating into an independent and dependent data set, creating my dummies and splitting my data again into 70-30 of train and test. But this time it is not the original one, it is the feature engineered data. Now let's build a model now. So I'm building my linear regression model again. And once the model is built, I'll go ahead and predict it on the FTE train and FTE test, which is the feature engineered train and the feature engineered test. Okay, so I've got my predicted values over here. And now I can calculate my R square, giving my feature trained and feature trained predicted for train and test both. So when I print this, I see that my R square is somewhere approximately 0.57 on both train and test. So what do I notice here? If you remember, if you look at the original data set, you would see that the R square was 0.54 on the original data set. We just did a few changes, right? We created new variables. And with those variables that we created, we got an increase of 3% variance explanation in the data, right? So no changes done, just a few features created, and the R square improved from 0.54 to 0.57. Let's look at the RMSE. So I'm looking at the RMSE, fine, 0.48, 0.48. So overall, the models are not overfitting because the R square of train and test is similar. The RMSE is also very low, good. So let's go ahead and compare the results. Okay. So when you compare the result, if you look at the original data, the R square on train was 54%, while if you look at the feature engineer data, it came to be 57%. If you look at the R square of test, it was 54% on the original data, but on the feature engineered, it became 57. So you can see that the model is not overfitting on the feature engineered data. And also what you notice is that the results are good, right? They have improved from the original data set. If I look at the feature engineered data over here, the train RMSE and the test RMSE, I do see that the results of the train and the test RMSE are higher on the original data as compared to the errors which have reduced on feature engineered data, and the R square has improved too, which we just saw. So what we can say here is, if I'm doing some feature engineering, right, my R square did improve, my errors did reduce. So it does mean that when I'm doing feature engineering, the chances of me getting a better model, enhanced interpretability, and a better generalization is much higher than compared to the original data set. But again, as said, I can go ahead and create multiple features, but whenever we are creating features, remember that it should be in sync with functional understanding of the business, because you don't want to end up creating features which are not, you are not able to explain to business later on, right? So this is what we have, guys. Thank you everyone for watching this video. Please do like, share, and subscribe if you have liked this video. See you again in the next one. Thank you.